So, the next what we are going to study today is the another kind of MAC protocol, slotted aloha. If you remember, in the last class we had some assumptions for the MAC layer protocols when multiple nodes are trying to access the same channel, and the one of those assumption is the slotted timing, synchronized time synchronization, continuous timing and the slotted time. In a continuous time, there is no synchronization of the timings among the or the timers among the multiple nodes connected to the network. But whereas in case of slotted aloha or the other kind of time synchronized system, the whole of the all the nodes connected to the channel are having a global timer, and that timer is divided into number of time slots, you can say, is divided into number of time slots. And any node who is ready to transmit can begin its transmission only at the beginning of a time slot. Let us say X is a node who wants to transmit, and he can transmit only at the beginning of the time slot. If someone is ready in between any of this duration, then he has to wait till the beginning of the next time slot. That means any transmission or the capturing of the channel by the nodes is possible only with the beginning of your time slot, and all the nodes are having a synchronized or a global timer for them. That is what it is, slotted aloha. Now, what happens, what is the benefit of doing this? Let us say your timer starts, this is at 0th second and this is at the 5th second and 10th and so on. So, when a node X is ready to transmit, it now starts from the 0th second and it knows that till the 5th second, no one is going to disturb the channel or no one is trying to access the channel. So, this much of period is now free of contention or free of any kind of collision, for which the node X is the master of the channel and he can transmit, right. In earlier stage, in comparison to the aloha, what was happening, there was a random waiting time and we are expecting that the random waiting time will give a sufficient time period by which the node will be able to transmit. But here there is a fixed time period, the duration of a slot during which a node can transmit without any collision with the other nodes. So, when Y is ready at the 3rd second, he cannot transmit because the slot has already begun. Now, he can only start at the 5th second, and during 5th second, if let us say X is not completed, X transmission is still going on. Now, there could be a collision at 5th second, right, because Y is ready at the 5th second and X was given the timer from 0 to 5th second to finish its transmission, but X had a huge data. So, it could not finish within this 5th second. So, what it will do? It will continue further, but the next station is allowed to transmit at this point and there becomes a collision here. But the probability of the occurrence of the collision is definitely less in comparison to the probability of collision in case of aloha, or it is a pure aloha. You say this is a pure aloha and this is the slotted aloha. You have a fixed time period for which none other are disturbing. So, that could be a possible case when the node can finish its transmission. If not, then there comes in possibility of collision. And when there is a collision again, if the collision occurs here, then the same waiting of the random time period takes place. Random waiting time and the whole process will be repeated. That means the occurrence of a collision lead to a pure aloha case again. Pure aloha means they wait for the same random amount of time period and again they start the process. If the timer expires in between any time slot, again they have to wait till the beginning of that slot. That means there is still a collision, I mean still there is a contention, and once someone wins the channel or gets the channel, gets a fixed time period to have a contention free transmission. If it finishes by this period is fine, if it does not, then there may be a possibility of occurrence because someone else will be ready by that time to transmit. So, definitely the efficiency of your slotted aloha is more than the efficiency of your pure aloha. How much? We have to calculate that, we will see that, right. This is what is your slotted aloha, having a slotted time slots and the node permitted to transmit only at the beginning of a time slot. Now, what would have been better case in this situation, if you can imagine? How the situation would have been better? If the node who is getting ready at this time, let us say y, let us say your what we say x is transmitting at this point and you have the different slots. Let us say x is transmitting and the transmission still continues and y gets ready at this point. As per the principle of aloha, y can transmit because he is ready with the data. But it would have been decent if y would have sensed the carrier to see if the channel is free or not. If someone is transmitting or the channel is busy, rather I should not transmit, I can defer to the next time slot. That would have been a more decent way and your collision, chances of collision would have been reduced a lot. So, this is again a mechanism or a provision that all the nodes should have, what we say is carrier sensing. If you remember the last assumption, that nodes have a provision of carrier sensing. So, aloha and pure aloha and slotted aloha, they do not have the provision of carrier sensing, but there are certain protocols, we say CSMA, carrier sensing multiple access protocol, carrier sensing multiple access protocol. Now, what this protocol does, when the station is ready to transmit, instead of just pushing the data to the channel, it tries to sense the channel. That means they understand or they try to understand what the other nodes are doing. Let us say we have a channel, one node x is ready, another node y is ready here. Now, x has a data to transmit. Instead of just releasing the data, what it does, it sends the carrier, because it is connected to the channel, it checks it. If it finds there are certain signals are being transmitting through the channel, definitely it gets back a collision or a kind of feedback message. It understands that the channel is busy, so I should not transmit now, right. If the channel is free, like when it sends a beacon and gets back the beacon in the undamaged condition, it understands that there is no signal in the channel and the channel is idle. Now, it releases its own frame to the channel, correct. Now, the channel becomes busy and it is now transmitting to the destination. At this point, let us say y is getting ready to transmit. So, what y does? It senses the carrier, and when it senses the carrier, it sees that there are certain signals which are already in the channel. So, what it does? It waits for some other time or it defers its transmission. It has to transmit. Now, how long it should wait to transmit? Depending on that, again your CSMA protocol, or what we say, this y now persists to get the channel. Now, y persists to get the channel. So, how it persists? Depending on that, your CSMA channel, a CSMA protocol is classified into two types of transmission protocols or MAC protocols. We say they are the persistence and non-persistence CSMA protocols. Persistence and non-persistence protocol. Again, the persistence is classified into 1 persistence and P persistence. To understand this, let us say we will have a flow diagram of a persistence channel. Let us say persistence MAC protocol. Let us say a node is ready. A node is ready to transmit. So, when it is ready to transmit, it checks the, sends the carrier to find whether the carrier is busy or idle. If it finds it busy, what it does? It again senses it. If it is yes, it continues to sense the channel to find its busyness. If it finds it, no, it is not busy, that means it is idle now. What it does? It starts transmitting, transmits. Now, during the transmission it may happen, there occurs a collision. How this collision occurs, we will see. Why this collision? After sensing the carrier also, how you say that there is a collision, right. So, it finds the channel is busy, idle, and now it is transmitting. Now, during the transmission, if there occurs a collision, if yes and if no, then you have a successful transmission. If yes, what happens? Again you go back to a random waiting time and it starts the whole process again. It becomes now ready and the process is continues here. This is what is your, you can say, persistence MAC protocol. Now, why you say it is one persistence and why it is P persistence? One persistence, when it finds that the channel is idle, no means it is idle, right. When it finds the channel to be idle, it immediately transmits with a probability of 1. That means I am sending, I must send when I get the channel. So, as soon as it finds the channel to be idle, it transmits the data to the channel. That is what is one persistence, assured transmission of the data. But in the P persistence case, what it does, the probability of transmission is P. It gets the idle channel, but still it is not, it does not want to transmit for certain reason. What it does, it defers to the next slot, either it can transmit with a probability of P or with a probability of Q, it may defer, and this is equal to 1 minus P. It defers its transmission for the next slot. It is like you enter into the room, you find that all the lines or chairs are occupied, right. Some other class is going on. So, what you do, you are interested to sit in the front line. So, you wait there till the front line is free or any of the seat is free, and as soon as it is free, you occupy that. That is persistence. And what is one persistence? If any chair is free, you occupy that. But it is P persistence, a chair is free, but again you do not want that chair, you want some other chair in the same row. So, you defer to the other chair and you give that chair to somebody else, that is it. So, that is again P persistence. You are getting the chance, but again you have some options, so you are not occupying that. That way it can handle the, it can occupy the channel to transmit, right. Now, there is a question here, you say you decide, a node finds the channel is busy or not. If it finds it idle, then it transmits, fine. When it is transmitting, definitely it is occupying the channel. Someone else who will try to occupy will get a busy tone and it will not transmit. So, where is the question of collision comes then? Why collision again in this situation? Can anybody say why there is a collision again? You mean to say when it senses the channel, it may get a wrong response, right. So, it assumes that it is free, but it is not actually.
Because of the, you will check the channel is free or not. So, suppose there is a signal from node X and Y is sending, and with the interference of node X and the sending signal, it may receive a signal that is free.
Yes, that could be a possible situation, and what we say, the situation will occur when the situation can occur, when the propagation delay of any signal is high, right. Let us say we have a channel like this, one node is transmitting X and its propagation delay is very slow. Just immediate after this, another node Y gets ready and Y senses the channel. By the time Y senses the channel, X signal has not yet reached to Y. So, there is a gap. X has started transmission, but the propagation of the channel or propagation of the signal is so slow that it has not yet reached to the area of Y. So, when Y senses the channel, it finds that it is idle. So, what it does? It transmits its own frame, and when it comes and this one, there is a collision here. So, one possible case is when the propagation delay is high for transmission. At that time, though both of them have checked for the idleness of the channel, but still there occurs a collision. Let us say the propagation delay is 0, 0 means very less. Still there will be a possible case when there could be a collision. Let us say X is transmitting, another second case is, let us say X is transmitting and Y and Z both are getting ready, and when they get ready they sense the channel and find that the carrier is busy. Y finds the carrier busy, Z finds the carrier busy. So, what they do? They persist for the channel, and as soon as the channel is free, as per the flow, they will start sending their data. At that time there could be again a collision. That means because it is a contention based protocol, there is always a high probability of resulting a collision, and this collision has to be avoided by some means. Either the propagation delay is high, you get a collision, propagation delay is very less, still you get a collision. The reason is that both of them are persisting and they get the collision, right. So, this is a kind of what we say is a persistence protocol. Now, before going for how to avoid this collision and all, we will see another kind of protocol, that is the non-persistence one. What happens in the non-persistence protocol? In the non-persistence protocol, again the carrier sensing takes place, all the process that comes to the idleness, busyness, everything that remains same, but only thing is that if I check for the idle, if it is yes, then transmit. If no, what was happening? It was again continuously persisting. But in the non-persistence case, if it is no, then the station resumes its own work. He can have his own work. Instead of persisting the channel continuously, it can do its own work, and after certain time interval, it can go to check whether the channel is idle or not. It is like you find a seat occupied, you go and do your job, and after some time you come back and see whether it is idle or not, it is free or not. If it is free, you occupy, if it is not, you do not. So, by this, how you say which one is a better option, the persistence one or a non-persistence one? Depends on the scenario or the requirement. If you go for non-persistence, when you do not have a prioritized job or you do not have any urgent transmission, you can wait for your time, you can take your time, you do other job and find out. But when you have some data to be transmitted immediately, you need to have a persistence timer, persistence protocol to check whether the node is, the channel is free or not continuously, and as soon as you grab it, you transmit the packet. So, this is completely scenario dependent, saying which kind of protocol has to be used by the network designer. That's what is your contention based protocol, maybe Aloha, maybe slotted Aloha, maybe your carrier sensing multiple access CSMA. There is another variation of this protocol, usually we say that is CSMA CD. What we studied till now is actually CD. CD is collision detection. It is actually collision detection, meaning any node who is transmitting has a provision to hear back from the channel. Like someone is transmitting means it is releasing the frames to the channel, and during the transmission it finds that there is a collision to one of my frame. So, instead of releasing all the frames to the channel, it immediately stops to save its own transmission cost, the bandwidth, all the resources and everything. So, CSMA CD is one of the version of the CSMA, carrier sensing multiple access, when after the collision is detected, immediately the transmission is stopped. We say this is also a contention based protocol. So, Aloha, slotted Aloha, CSMA and CSMA CD, both are, all three are the contention based protocol, and with this now as a network designer or any protocol designer, you can think of a protocol or any MAC protocol. If you model that, you will see if you have one successful transmission, of a frame, then after this definitely there is a certain period over which the contention takes place, right. Maybe it is a slotted time, maybe it is a carrier sensing, maybe anything. If there is one successful transmission, soon after the transmission is over, definitely there is a contention in which multiple nodes again try to contend to get the channel. So, this period we say is a contention period, and after during this contention period somehow one wins and gets a chance for another successful transmission of the frame. So, the whole of the transmission or communication timing is modeled as like this: a successful transmission followed by the contention protocol, then again a successful transmission, then again a CP and so on. So, it is your job as a protocol designer to decide how the contention could be resolved and you get a successful frame transmission time. Usually this period should be much more than this period, right. Otherwise there is no efficiency in the transmission. If the most of the time is for your contention resolving, there is no point. You should have a longer transmission period and you should have a shorter contention period, and during that contention period you apply some algorithm, some logic, so that sooner you get this successful transmission period and you have a efficient transmission. How this contention could be resolved? As we discussed yesterday, one kind of transmission protocol, the MAC protocol, is a contention free protocol or collision free protocol, right. There are certain protocols, MAC protocols, they are totally contention free or collision free. The reason is that during this contention period they implement the algorithm or they apply some algorithm so that you get a faster successful transmission, and during the beginning of this period at least all the contention is resolved. That is what is your contention free or collision free protocols. And remember, all these protocols are your distributed. If you remember, distributed means what? Every node has to execute or have to work on that same protocol. It is not like central, one will take the responsibility and others will enjoy. No, everyone has to take part in this contention, everyone has to take part in implementing this algorithm so that one of them wins and gets the channel. So, they are all distributed protocols. Now, how the contention free protocol works during the contention period. So, we will now talk about only the contention period, we will not talk about the successful transmission. It is by default assumed one wins gets the successful transmission, right. So, one of this contention free protocol is a bitmap protocol. Bitmap protocol. What this protocol, in this protocol what happens, your contention period is divided into number of slots, time slots, I mean to say time slots, they are all the time slots, and this number of time slots is equal to same as the number of nodes present in the network. We are talking about the LANs, because we have not yet thought for the scalable network or a bigger network. What we are considering is a small LAN and a wired network, right. So, what we have now, the total, if we have n number of nodes, then your total time slot contention period will be divided into n number of slots again. If you allow maximum contention period for your network to be 5 seconds, then accordingly, and 10 nodes are connected, you give 0.5 seconds for every node or every slot, and each slot is numbered with the same as the number with your number of nodes in the network. During the 0th time slot, this is mapped to the, or this is allocated to node number 0. If node number 0 is ready with its data to transmit, what it does, it transmits a 1 into its own slot, saying I am ready to transmit, I am ready with my data. During the next time slot, node number 1 gets chance to say whether it is ready or not. Let us say it says no, I am not ready with my data. So, puts a 0 into its slot. The other one similarly 1, 1, let us say 0, 0, all zeros, they are not ready to transmit. So, now you have multiple slots according to the number of the nodes, and they say whether they are ready with their data to transmit or not. That means all the nodes connected to the network has the knowledge of their neighboring nodes. They know whether they are ready or they have the data or not, right. So, now after this contention period is over, you have the successful transmission timing, and during the successful time, or you can say the frame time, rather I will say the frame time. This is contention period and this is frame time, frame transmission period you can say. First, who will get the chance to transmit? Node number 0. So, he does its transmission. After the transmission of node number 0 is over, node number 2 gets the channel and he completes its transmission, and then 3 gets the transmission time and the transmission is over. So, whole of the time is your successful timer. Now, none of them can interfere because they did not reserve their slot or they did not reserve the channel when they were given with the option whether you are ready or not. So, now see, during this frame timing or the transmission time, you do not have any collision at all. So, this is absolutely collision free protocol or contention free protocol. So, whatever contention that will take place or whatever reservation they will do it during the contention period, and finally they book the channel and they get the channel for their successful transmission. Is that this one better than the earlier one? Once resolved, no contention, and you can have a longer transmission time for all the nodes who have their data ready with them. Now, let us assume the node number 1 gets ready soon after its chance is over. Now, it gets ready. What he has to do? Let us say the timer is now at node number 4 and at that time 1 gets ready, no chance. What he has to do? He has to wait till all the reservation of the contention period takes place, then whole of the transmission takes place, then again its own slot come to book its slot. That means, if a node has got high or heavy data to transmit, it always gets the transmission time or it always gets the channel to transmit, and a node who has less prioritized data or less data to transmit, he can wait. So, this is one of the collision free or contention free protocol, that is bitmap protocol. Another protocol is there similar to this contention free protocol, its name is binary countdown protocol. Binary countdown protocol. What happens in this protocol? Every node in this protocol has got an address, or you can say the unique address, right, and the unique address length is same for all the nodes. Let us assume that we have 4-bit addressing for all the nodes. We have 4 nodes, let us say A, B, C and D, and they have the addresses. So, I will say 0, 0, let us say 1, 0, let us say 0, 1, 0, 0 something, 1, 0, 1, 0, and then let us say 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, let us say. So, they have their address schemes and 4-bit addresses are being used 0, 1, 2, 3, 4 bits. Now, in this process, in the binary countdown method, what happens, all the nodes they enter into a process of bidding there, or they announce their addresses starting from the high order bit, the most significant bit, this bit. So, they address or they broadcast their addresses, and all those addresses that is being broadcasted or announced by the nodes, they are logically odd, or you can say Boolean odd. So, what is the outcome of this first digit MSB when they are Boolean odd? Outcome is 1, right, and every node then checks with the output of the result with their corresponding numbers or bits they have announced. If they find their result is higher than the number that they have announced, what they do, When this finds the result is 1 and this finds the result is 1, what happens? They immediately withdraw. They withdraw from the bidding, right. So, what happens? Now, this node and this node, both of them withdraw. That means, during the second announcement, they send nothing. So, who else enters into the bidding? Is only these two nodes. The second high order bit is 0 and 0. What is the result? 0. So, whatever they have transmitted and the result they match. So, there is absolutely no problem. Now, what happens? They go for the second bidding, third bidding. Again this fellow sends nothing, this fellow sends nothing. Now, again both of them are odd, right. The result is again 1. So, both of them we know they can enter into the last bidding. Again this sends nothing. Now, this comes when these two are odd, the outcome is equal to 1. And when it comes to 1, now who will withdraw? C node will now withdraw. So, who wins is now the node number D. So, now node number D wins because it has a higher address. That is the drawback of this one. Any node who is having a higher order or higher address will always win, but the objective is your collision is completely eliminated. So, the next transmission will be by the node number D only, and after this transmission is over, you can have again the contention period, you can again enter into the bidding and all those. The process will continue. This is what is your binary countdown protocol, which is a completely collision free protocol. So, your contention based protocols Aloha, slotted Aloha and CSMACD. Contention free protocol, binary countdown and bitmap protocol. There is always a trade off, a choice of the network designer or a protocol designer to decide whether I can have a longer contention period, I can have a shorter contention period, I will give the priority to a high order address number or I will give a priority to the low order numbers. So, in this situation, when you see that the high order addressing number gets the chance always to win, what the network designer can do? You can have a address generator algorithm, right, and a node having high priority data can have a high address, or a node having huge data to transmit can be assigned with a high order address, so that he gets the chance mostly and does the transmission accordingly. So, you can have a reservation kind of time. If you say no, I do not have time for reservation, that means if I have let us say a situation you have a scalable network, 1000 nodes are there, every node has to be given some time for reserving in the bitmap. So, what you can have? You have to give a longer contention period because every node will have the time. So, 1000 slots has to be there. Whether you are able to afford that much of contention period, if yes, you can go for bitmap, if no, you can go for a binary countdown. And again binary countdown, how much time it is required for this logic to be or the algorithm to be implemented, that is to be chosen. So, it is all scenario dependent. You have been given with lots of choices to see what kind of network you have, what is your requirement, and depending on that you choose a particular protocol so that you can have this. If you do not want to compromise with the collision or anything, you should go for a collision free protocol, provided you have time for executing this contention period. If you do not afford that period, you go for a contention based protocol. Again, there is a high probability of collision all the time. So, you decide which kind of protocol the designer can opt. Usually army or defense field, they do not have the time for contention, reserving contention and all. So, what they prefer? Contention based usually. But when the real time transmission takes place, any video, anything is transmitted, you always opt for contention free protocol, because the reliability or the content of the data transmission has to be is more important than the time. So, depending on that scenario, you can have this protocol. So, the another kind of binary MAC protocol is left, that is the round robin or the token based MAC protocols. We will see them in the next class.